Wonderful. While I present, I won't be able to see you, unfortunately. So if there's important information, please feel free to interrupt me at any point of time. So today I'll be talking about causality for neuroscience and beyond. And this issue of causality is an issue that was probably closest to my heart for the last couple of years. Oh, hey, and I totally forgot. Like, yeah, thanks so much for inviting me. It's a great honor for me to be speaking in Iran for the first time in my life. But let me go forward here. Let's talk about causality. So the first one is, what is causality? I find that this XKCD cartoon is the best introduction to the idea of causality that I've ever seen. Um, I so the guy here says, I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. What is so wonderful about this cartoon is that it really shows that the person understood causality. And we'll see in a few slides while that is. But the broad definition is just the relationship between cause and effect, the principle that has a cause. So, but let's make this like into a precise definition that we could meaningfully talk about. Let A and B be events. Now, what I mean with events is maybe A is one neuron spikes at time t, and maybe B is the other neuron spikes at time t plus 1. It could be that A is I smoke, B I get cancer. Now, the definition of causation in that causation exists is if we had changed A to A star. So we reach in, change this variable or this event A to A star, then the probability for B would be different. Why do I say the probability for B would be different instead of B would be different? Well, in lots of situations, things are probabilistic. You know? Like if I do smoke, if I would smoke, I don't smoke, but if I would smoke, then there's a certain probability that I'll get cancer. If I don't smoke, there's another probability that I'll get cancer. Importantly, we now know that these two probabilities are different. Therefore, smoking has a causal effect on cancer. Now, I first want to highlight how thinking about causality has gotten to be very popular. So what you see in orange here is the number of neuroscience papers. This is just Google Scholar. So there is a bias that the most recent few years are still missing some of the articles in Google Scholar. I think the baseline effect is real. So here you see the number of neuroscience papers per year. I do believe that that number peaked sometimes in around 2011, 2012 or something like that. But if you then look for papers that are about that contain the word neuroscience and also contain the word causality, you can see that that has steadily been rising. In particular, given that recently the number of neuroscience papers has been going down, the ratio of papers that are also concerned with causality is going way up. So causality is becoming a popular topic in neuroscience. And it's a popular topic everywhere. And that's why I'm excited to be telling you about causality today. So let's think about our role as scientists. The world affords us humans a set of actions. There's certain things that we can do. What does it mean to be a good human being? Well, choose the action that makes the world better, which is fundamentally a counterfactual question. What would happen if I would do action A? And what would happen if I would do action A star? And action B is then however we define the world being better that comes down there. So the very question of what it means to kind of live a good life is a causal question. So now let me just review briefly how causality, through basically all branches of human endeavor is a central topic. And then we'll talk a little about getting more intuition about causality, and then I'll wrap it back into neuroscience. So let's talk about medicine. Medicine is full of causal questions. What we want to do is, what can we tell people to do, or what drugs can we give to people so that they'll be better? For example, if we do physical workouts, does that let us live happier and longer lives? It's a central question. We don't care if people who live long or who live happy lives, if they do exercises. What we care about is if we convince people to do exercises that currently don't do exercises, will they live longer, happier, and healthier? So it's a causal question that all of medicine is about, or virtually all of medicine is about. Social sciences, you can say, if we would increase taxes and would give every person enough money that they can live a decent life from, a concept known as basic income, where every person gets a certain minimal amount of money, would that make the world better? Well, some people say, well, if we had that, people would stop working. Other people say, well, actually, no, they would mostly be working just as hard as before. My wife, Joanna Marinescu, does a good amount of research on that. The question is, what's the causal effect of introducing such things? Same thing in neuroscience. No? In neuroscience, we might ask, how does a neuron influence causally another neuron? Because that's kind of the stuff that our theories are made out of. Or alternatively, we could ask, how do brain regions influence one another? Or we could ask, how does a pacemaker through an electrode can help, say, Parkinson's patients live better? So all of them are causal questions. In biology, we have causal questions. We have food chains. So every being in that food chain has a causal influence on all the others. And that is something that we want to understand as biology. Science itself can be seen as an endeavor where we are trying to figure out causal things in the outside world. And science itself can be viewed as a causal chain of things where we discover new things. Engineering, engineering is about making an outcome better. In this case, for example, allowing a monkey, or hopefully humans, to be able to use robotic devices to maybe feed themselves or interact with the world. It's also important in business. No? In business, we might say, welcome to our webpage. Click on the lawnmower button in blue. Or alternatively, welcome to our webpage. Click on the lawnmower button green with an arrow. What businesses often do is what's called A/B testing. So they randomly give half of their visitors this webpage with the blue thing, and randomly the other half that same webpage with the green thing. They can compare. Are there more people that will click on the webpage in the right-hand side or on the left-hand side? And so in businesses, people are usually optimizing something. Get me the maximal number of visitors, give me the maximal amount of money I make by selling a product. All of those are causal questions. And causality ranges across all the scales. You can say there's causality of molecular cascades within individual cells on the nanometer scale. There's causality at the level of cell to cell micrometer scale. There's causality between brain regions at the millimeter scale. There's causality within my body at the meter scale. There's causality in ecosystems on the kilometer scale. And there's migration of human paths in history that are at the million meter scale. So in any case, we have all these different spatial scales for that. So the question is, what are the general things that we can say? So in general, causal inference boils down to this question. I have a variable here, and I want to know, does this variable affect this other variable that we have up here? Well, how could I know? Well, I might observe some correlation. Whenever this thing is active or whenever this thing is big, then this thing is also big. is that enough for me to conclude that there's a causal chain from here to here? Well, actually, no, because there's this thing that's called a confounder. I have a variable that affects both of these variables, affects the bottom variable, affects the top variable. Now, if I see often that this one's active and this one's active, it could be because there's a causal chain from here to here. But alternatively, it could be because there's a causal chain from here to both of them. This is what we call a confounder. Now, a lot of people think about clever ways of thinking about this, but confounders are generally pragmatic. Now, you could say, well, what if we can use time? Now, maybe this variable goes up fast. Maybe if we talk about neurons, this neuron starts firing at some point of time. This neuron fires a little later. Shouldn't that mean that this neuron causes this one? Well, no, because alternatively, this neuron here could make this neuron fire, and then a little later the other one fires. So looking at time is not necessarily a way of getting out of the problems that we have in this kind of a system. Now, a lot of people, in particular those that think about machine learning, are like, oh, look, if we have confounders, we can statistically get rid of the effect of them. Now, if this variable affects both of those variables, and we know what this variable does, we can basically try and estimate these errors here and subtract them, and then in the residual, this confounder will be gone. And it's true. It's a great way of dealing with confounding. The only problem is there's this other thing, which is called a collider. The collider is a variable. There's a lot of versions of that, but it's a variable that is basically affected by this variable and by this variable. Now, if I correct for the confounders, my estimates get better. If I correct for the colliders, my estimate gets worse. The problem is that it's often very, very hard to know what's what. Now, like, think about brains. Let's say these are two neurons. How do I know that other neuron that I recorded affects these two and is not affected by these two? And even if it's not directly affected by it, there could be a chain going there. So colliders make it very, very difficult to correct for anything, because you can never know what's a confounder versus what's a collider. And this here, this slide this is why causal inference is something that is a scientific field. It has a very well-developed theory. It has a lot of people working on it. But it also highlights why this is so difficult. You know, there are these things, in particular, if we don't know the confounder, things are difficult. And if we know certain things, we can never know what's a confounder and what's a collider. So that is the difficulty the world throws at us. And all of causal inference research is basically, let's try and figure out how to do things about these. So now let's talk about confounding. How much do we have? There are cases where we arguably have no meaningful confounders. No, maybe you have a wonderful preparation. You just have one neuron in a dish and you see what it does. You inject electrical currents randomly through a pipette. No confounders. Wonderful. Atari games, arguably, it's essentially all observable. Randomized control trials, as long as there's no dropout. If you have a perfectly designed randomized control trial in good approximation, there's no confounders that are pragmatic. But then, of course, if you look at non-RCTs in medicine, I look at, do people who take vitamin D, do they live longer? Well, actually, probably yes. Does that mean that vitamin D makes you live longer? Well, probably no, because rich people tend to live longer, certainly in America, and they also tend to live vitamin D because why not? Like, the cost is irrelevant for them. So it will look like vitamin D is this wonder supplement, where in reality there's a confounder, namely socioeconomic status. Now, confounding with brains is particularly problematic because what we usually do in neuroscience is we record from maybe 1,000 neurons, or when we do fMRI signals, we get data from maybe 30,000 voxels or something like that. But the brain has 10 to the 11 neurons. So the activity of the brain lives in a 10 to the 11 dimensional space, which means that we have 10 to the 11 confounders. So getting to causality from brain data is very problematic. Now, before I go to intuitions, I want to briefly spend 2 minutes advertising Neuromatch Academy. It's a summer school. It runs this year, July 10th to July 28th, everywhere on Earth, and we mean that. Neuromatch is running on, I believe, 13 time zones. It is running in a lot of different languages. I believe we suddenly had people learning neuroscience at Neuromatch Academy in Italian and Arabic and Farsi and in German, I believe. So there's really all those different languages that are there in all those different time zones. And it's really international. People from all kinds of countries participate. And we haven't yet opened the application portal, but it's going to happen very soon. And you can already subscribe to the mailing list at academy.neuromatch.io. A good number of you might have heard about it because it was very popular in Iran this year. Now, the reason why I mention Neuromatch here is the next few slides is just an excerpt of the Causality Day at Neuromatch Academy. But it's the best description, the best intuition builder that I've ever seen for the role of causality. And of course, in parts, it's because I'm biased here. But people have this intuition that correlation and causation are something very similar. And I have that too. And I never quite understood why my gut feelings always correlation and causation is the same. But in reality, as a stats-oriented person, I know that they're not. So let's look at the most simple possible system. So we have an n-dimensional dynamical system. It's characterized by a vector xt, and the dynamics are just xt plus 1 is sigma of axt plus epsilon t. Epsilon t is just a noise vector that we add at every point of time. A is a matrix characterizing actual causal inferences. Not like the components of A says which component of this vector affect which other component of the vector. One way of thinking about this is that we could say xt could be the activity of all the neurons in a brain. It could be any other dynamical system, no? And this is just an intuition builder. Now, sigma is a sigmoid nonlinearity. It doesn't really matter. The results look very, very similar if you take it out. A is the n by n causal ground truth matrix. We draw it sparsely. Epsilon t is noise. We initialize at 0. And then you can say, well, here we have a system. Is in the system correlation roughly causation? Well, let's look at this. There's 2 ways how we can visualize causal systems. We can either visualize it as a couple of nodes, and we can draw arrows that indicate how strongly one node influences one another. Now you can say here, this node affects this node also affects this node affects this one affects this node, nothing else. We can alternatively write this as a matrix, where you can say we have neuron 0 here going to neuron 1, and neuron 5 going to 3 and 4, and so on and so forth. At the top, we have the ground truth causal connectivity matrix. This is really how strongly each dimension here affects every other dimension. What we have at the bottom is the delay 1 correlation between these vectors. Not just the intuition, the activity, the vector at t affects through A the vector at t plus 1. So if you want, if this thing is active at one time point, then we expect this one to be active at the next time point. And here you have the estimated connectivity matrix. This is really just the time delay 1 matrix. And look how similar those 2 matrices are. So it looks as if correlation is causation. And this is the kind of system that I can simulate in my head to think about it. I can be like, okay, now let's say I have 6 neurons, and now imagine number 3 is active, and then at the next time step number 4 is active, and I can think through it like that. And that's why my intuition is that correlation and causation is the same. But then why do stats-minded people always say that correlation is not causation? Well, what we're going to do now is we're going to use the very same causal generative system. Nothing changes in the equation, nothing changes in the way we make the matrices. The matrices are all made so that they're basically that the largest singular value is 0.99, but we generate them exactly the same way. Here we see what happens if we now have a big system generated the same way. On the left-hand side, you see the true connectivity matrix. On the right-hand side, you see the estimated connectivity matrix. As you see, I'm not drawing this diagram with the error. The errors are kind of pointless at this point of time. You wouldn't see anything there because it's just too many lines. But what you can see if you just squint at that, these two matrices look very, very different. So let's quantify it. On this axis, you have, I call it the number of neurons. It's the dimensionality of this dynamical system. But it could be the number of neurons that we simulate. On that axis, on the y-axis, you have the correlation of the A matrix with the R matrix. This is just really just a raw correlation of the flattened matrices. What you see, if there's a small number of neurons, they're very similar. You have a very large number of neurons, where large is already 100, then the correlation is very, very low already. So that means that for the kind of small systems that Konrad's head can fit, correlation is causation. That's why Konrad feels that correlation is kind of causation. But then if we look at all those complex systems that humans build at the moment, like the brain and the economy and politics and all that, that is millions of components, trillions of components. And in these systems, these intuitions that basically correlation is similar to causation, they're just no longer right. Now, what's the effect of that? And can we get an intuition for why this is? Like what I just showed you here, this is just a simulation. Like we put in a dynamical system, we simulate it, and we just find it gets to be different. Well, let's see why it gets different. So in the linear case, the economists have long worked with what's called the omitted variable bias equation. We have a system that is yi, that is xi beta. This part is the causal part. So the idea is that x and y are the things that I measure. And in this case, y could be the next time step signal, x could be the current time scale signal. But now we also assume that there's some signals, z, that we don't observe. And of course, we assume that there's noise. And if you do these things in high-dimensional spaces, usually people use u instead of epsilon, and I have no idea why this is the case. Now we can use linear regression. This is the equation we have for linear regression with the covariance matrix of x inverted times x prime, and then we have x beta plus z delta plus u. Now we can reformulate it. The expected value of what we'll measure is beta, which is the correct thing, which is great. But then we have a bias. The bias here looks just like this part. Now look at this. It's just, again, the covariance matrix of x times the covariance of x with c. Now look at this. This is so let's first make sure we understand that. So when people first see that, in particular if they don't come from a computational discipline, they're like, okay, Konrad, I need to then put more people in my scanner, or Konrad, I then need to record from more neurons. No, this is a real bias. This does not go away in the limit of infinite amounts of data. It would only go away if the variables that you do record from are uncorrelated with the variables that you don't record from. But they're kind of never uncorrelated, in particular not in the brain. Here's, for example, a nice Cohen and Kohn paper measuring and interpreting neural correlations. They find that the typical pair of neurons that they record from have quite considerable correlations with one another. So this is the omitted variable bias equation. It means that if you don't record all neurons, there's going to be a bias. Now let's think a little bit about the size of that. Now, like we have one term here, the X beta thing, which is the recorded parts. I told you, we record like order 1,000 neurons or dimensions of MRI signals or EEG signals at a time. How many terms are in this bias? Well, all the variables that we don't record from, that's 10 to the 11. So this bias has arbitrarily more components than go into this component. Therefore, we should expect that the biases are very, very large. The biases are probably so large that there's almost no signal in this anymore. Now, this is one way of thinking about it, which just says, if I can't record from all neurons, I can't estimate causality. But imagine, just imagine for the moment, we could record from all data. Not like technology makes wonderful progress. There's Stephenson's law. The number of simultaneously recorded neurons doubles every 6 years. It's gotten faster since industry got into it. So what if we could record from all neurons? No, in that case, for a given neuron, all presynaptic neurons would be recorded from. And we can actually, the Bechdel criterion is fulfilled, at least if we can do it fast enough. And sorry, brief apology. In the theory of causality, Julia Paul did a wonderful job at like laying out under which circumstances we can identify a causal effect. The Bechdel criterion means that if I want to know what's the effect of A and B, and I have all neurons or all variables that feed into A, and there's a few extra conditions, but under that criterion, that's called Bechdel criterion because those are the variables that go into the first variable. Under that criterion, I can figure out what the causal effect is. So in principle, we can do that. But let's look at the variance. Now, like what we want to do is we want to have an estimate of the neuron's weights or of the causal effect of the neuron that we always call beta here. We want that our estimator of beta is close to the actual beta. And the 2 norm feels like a good way of quantifying that. And we know from the properties of linear regression that, that this has 2 well understandable components. It has this right-hand component, which is P is the number of parameters that it has. And N is the number of samples that we get. And what do you know? We can get a sample every 10 minutes or something. If we have 1,000 inputs, it takes 1,000 times as long. If we have 10,000 inputs, it takes 10,000 times as long. So this is what this factor is. And then here we have this factor, which is the smallest singular value of the, it's the inverse of the smallest singular value of the X matrix here. Now, if the stimuli are white, then X transpose X is the identity matrix, sigma P is 1. Great. But imagine the stimuli were white. So X transpose X is the identity matrix, the expected value of that. How long would it take us per dimensions? Well, depends on how you think about it. Neurons on average spike once per second. So if you want 10%, you need 100 seconds per input. And you have about 10,000 synapses for cortical neurons. So you can say 6 days if we calculate it like that, if the stimuli were white. But keep in mind that the stimuli in this case are just the other neurons. But if all neurons were uncorrelated to be white, then we would have nothing to observe anymore. So linear regression would make no sense. So we would need to deal with like actually occurring statistics of neural firing. So What we find is there's many names for that, but if we apply dimensionality reduction to neural data, we find that there's some dimensions with very large singular values and a lot of dimensions with very small singular values. So here you can see, for example, a figure from a Stringer et al. Paper, where you have how many principal components you use to reconstruct something, and or like what the index is of the principal component. And on this axis, you have the variance that they explain. And there what you see is that it looks like, in good approximation, it's a power law. It's linear in log space. On this axis, and what you see is the small singular values are factor 1,000, maybe more, depending. And this was recorded from a relatively limited number of neurons. So the small singular values are very much smaller than the biggest singular values. Now, let me just share that this is worrisome because we see here the inverse of this in our estimate. So why is this what's the intuition for that? So if we have a small singular value there, it means that imagine we just had two neurons. The small one would be, and let's say they usually go up and down at the same time. A small one would be the little variation that we have relative to one another, and the big singular value that's going up and down. But that would make it very, very difficult to know if there's a causal effect, is it of that one neuron or of that other neuron that is heavily correlated. And then it means that when we solve the inverse problem, we are multiplying with the inverse of the covariance matrix. And in that term, then it means that the difference between the two neurons, the thing that maps onto the small singular value, is going to have whatever noise it has on it from the recordings. That noise will be blown up by, well, 1 over the singular value. So it will be blown up by a very large value. So brief zoom out, what does that mean? That means that even if we could record from all neurons in, say, a mouse, it's very unclear. No, because here, instead of 6 days, it would now give us, say, 1,000 times 6 days. That's 20 years if I roughly calculate that rate. That's not a period of time that I could meaningfully record from. And that means that even if we could record from all neurons, we might be unable to estimate how all those neurons are influencing one another. Good. So now I just told you that in lots of cases we can't get causality. And now I want to give you examples of where sometimes we can actually do get causality. To be clear, in most cases from observational data, it's impossible to get at causality. If you stick a few electrodes into a brain, unless very strong assumptions are given, like, say, very high tempo precision and very, very sparse firing, you will be unable to say how causally things work there. But sometimes, just sometimes, there's the opportunity for what's called a quasi-experiment. In the causal inference literature, when people say experiment, they mean that it's something where I randomly perturb. A randomized control trial, that's an experiment. An experiment, how neuroscientists see it, with just like an open body of an animal, can be horribly confounded. Observational data is when I can't randomize. Quasi-experiments is kind of when the world randomizes things for me. And we built a little package with which people can play with that. Here's a tag if anyone wants to go there. Otherwise, it's easy to search for it. It's all linked from like the Leo Unger paper. So let's talk about cases where we can learn about causality. And I will go through the case of regression discontinuity here. In America, there's this thing called Certificate of Merit. Every student takes an exam, and it's a nationalized exam. Everyone does the same thing. It's it's roughly continuous because there's a lot of questions that they ask. And now the idea is you have an exam score. There's arguably some randomness on it, and now you can say that if you're below that threshold, the probability that you're going to get the certificate of merit, which is really just something for your CV that says like, no, this person is officially awesome because they get such a good grade. And then, of course, the probability of getting it is 1 once you're above that. Now, let's first plot two hypothetical lines. Imagine we would just randomly sample people out of the population. They don't take the exam. We'll just say, look, here's a certificate of merit. In that case, you can say there's a hypothetical curve where if we just choose random people. Now, it's possible, we don't know how that curve looks like. It could be that the people that are far out here, that they're very brilliant, they don't need it. It could be that the people here, it's just a shame for them, they don't enjoy it, or maybe they do enjoy it. What do I know? We don't know much about that curve, but I'll tell you a few things that we do know about the curve. And then you can say, alternatively, there's also another hypothetical curve, which is what would happen if just like we took anyone and just said, like, regardless of what happens in the exam, you're not going to get it. And now you could say on the y-axis, I should have said that earlier, is some measure of future achievement. Maybe the grades you get, or like if you get stipends, could be anything. Now, keep in mind that we only ever observe the green curve on the right of the threshold and only ever observe the red curve to the left of the threshold. But there's one thing we know about these curves. They must be smooth. Let me highlight why they must be smooth. There's arguably a real randomness process in there. Randomness in the sense that, like I take the same exam 10 times. Sometimes I'll be 48, sometimes I'll be 55. I never had like very, very good grades. So in any case, there's going to be, if there's noise on the exam score, there's noise for this method on the x-axis, the curves must be smooth. Now that means that we can, because if they're smooth, evaluate in the vicinity of the cutoff. What's the causal effect of getting that? Because within that vicinity, you can say, if I'm left or right of the threshold, given that there's some noise on it, it's really random. There's a technical term, it's called as good as random, and it's very well defined. And under those assumptions, you can prove that you can produce an unbiased estimate of not the causal effect, but of the local average treatment effect, which is like the local version of the causal effect. Now, here's the first paper that did this. This is the classical Thistlethwaite and Campbell 1960 paper that did exactly what I told you. They take test scores here from those from the national examination. They took the percent of students winning a scholarship on the y-axis. They take who in G here, whoever wins, how many people win a scholarship, and here they take however many people win a prestigious scholarship. Now, what they fit to that is they fit a constant plus a constant times the treatment. This is like 0 here and 1 there. And then they have a linear slope here, and you have a linear slope there, and then they have noise. That's what they fit to it. And what they do find is that adding the certificate helps you. Interestingly, it primarily helps you in the vicinity of the threshold. Look at that. Once you go really far away from it, the people that are like very brilliant, for those people, apparently it doesn't have, like the effect goes down, or like the outcomes go down. It might just indicate that people who are very, very good scoring maybe don't take stipend scholarships. Maybe they live a different life. In any case, that's the classical study here, and importantly, it's the existence of a threshold that allows us to say if there's a causal effect. Now, here's another example of that same idea. Does the class size matter? Like, It turns out that Israel has this rule that no class can have more than 40 pupils, which produces a discontinuity. If you have 41 people in the school, you have two classes. If you have 39, you just have one class. What that study nicely showed is that, yes, small class sizes are really good for students. And I should say this whole idea of regression discontinuity designs, which is a quasi-experimental technique, has a very well-developed theory behind it. For example, if there's cheating, maybe, I don't know, rich people get to retake the exam, then the method is no longer correct, but we have ways of looking if that kind of cheating happens. There's also in the method, as I sketched it to you, we assume that there's a hard discontinuity. You always get treated if you're above the threshold, never get treated below it. There's ways of like allowing that to be fuzzy. For example, my group has been very interested in medical applications of that, and in the medical domain, well, doctors aren't always perfectly compliant. Now, I want to briefly skip over this because I wanted to mention the last thing. We built some theory of regression discontinuity as a theory for learning in neurons, where you can say the spiking threshold for a neuron is like an RDD, and we could show that you can speed up learning with it. Now, let me spend the last 4 or 5 minutes. I don't want to run overly long. I always prefer talking about questions. Can us neuroscientists hope to get at causality? So that's often something that I hear. I'm like, look, what are you doing? It's not getting at causality. And then people are like, look, if you give me a way of getting at causality, I'd be happy about it. But I don't see how to do it. And of course, like, people just so deeply want causality. Like our models are all about causality. Medicine's all about causality. Can we even get there? I think as neuroscientists, we can. And I think as a field, we should. So here's C. elegans. It's a roundworm. It has 302 neurons in the hermaphrodite stage. The nervous system is very similar across worms, so much so that each of these 300 neurons kind of have a name, and you can label them, and they have the same color in every worm. And so we really understand a lot about it, and there's also evidence that the way the worms function is very similar across worms. Now, briefly, what can C. elegans do? Like, I don't want you to say, oh, yeah, that's just C. elegans. Well, C. elegans only has 302 neurons, but it can fight competitors. It can escape from danger. It can avoid bad chemicals. It forages for food. It mates. It adapts to changing mechanical environments. Their lives are like pretty rich if you think about it, in particular, given that they just have 302 neurons. And we can record essentially all of them, and we can identify the same neuron across neurons, and we know the connectome at the moment. Not only that, but we'll be able to do connectomes at exceptional precision with information where the molecules are. So within like 2 orders of magnitude, the number of molecules in C. elegans is the same as the number of synapses in the human brain, which kind of gives you the scale of how incredibly smaller, at least, it is, and how much more doable it is. Now, to be clear, it still needs stimulation. I showed you how to do power calculations for causal inference if you fully record from. So the covariance matrix normally is still there's still low dimensional dynamics, which would mean a bad condition number, which means that probably basically the sigma p would be very small, therefore we couldn't be good at estimating that. Now, but if we stimulation can basically add a baseline of white noise to it, which adds the identity matrix to it, which means that all these sigma p get to be much higher, and it will look the effect will be that it doesn't go down like that, but that it like stays up at some level. Which is great because we can really understand what stimulation would do in this domain. Now, to be clear, neurons are still nonlinear, and probably it's not enough to just say every of those 302 neurons is a weighted average of what the presynaptic neurons do. There's probably almost certainly going to be interesting nonlinear interactions. So you'd probably want to at least be able to stimulate every pair of them, um, or potentially stimulate lots of subgroups. Now, like, it could still fail because there's still a lot of parameters for that, and we don't know how complex a neuron is. You know, like, if neurons in C. elegans were mostly linear, then this is all very easy. If they're arbitrarily nonlinear, say they calculate the parity function on its synapses, then this is all entirely hopeless. But depending on how you do the power calculations, you might need about 10,000 worms. You'll have roughly wide spectrum through stimulation. If you say it would take 1 minute if you only had one synapse, instead it would take, and let's say we bring this sigma p to the -1 to 10. In any case, like first order approximation, and like this will be off by an order of magnitude, roughly 2 years, 24/7, every week of the year. This is something that if we come together as a larger community across many labs, this is absolutely in the doable range. We can do parallel data acquisition. We can estimate the I/O functions of every neuron, where we can say that we take the mistakes in our model fit and average it over time points and sessions, all the worms, all the stimulation, everything. And that way, we should be able to learn basically good models of the input-output function of every neuron, and then put all the neurons together. We're going to get causality, and hopefully that might allow us to simulate a nervous system, not of a human being, as Henry Markram promised us a couple of years ago, but of the humble roundworm C. elegans. And that would be very impressive, and I would feel very entitled to retire at that point of time. Now, so let's simulate a whole nervous system. So I think real-world questions tend to be about causality. Neuroscience questions are about causality. I didn't talk much about it, but causality and machine learning really have largely overlapping problems. There's so much to learn. For people interested in causality, I want to just briefly plug the CLEAR conference, which is a nice new conference in that area. And otherwise, well, thanks so much. Oh yeah, and of course, I didn't do any of that work, but it was all done by my wonderful lab full of wonderful students. And I so greatly feel blessed by working with so many wonderful people in my lab and from many countries across the world. And thanks everyone for listening.
Thank you very sorry. Thank you very much for the interesting and exciting talk. We enjoyed a lot. So here we take questions from the audience. Yeah, here's one question. Please give them the microphone.
What about now?
Can you hear the questioner's
I,
question?
I I can hear the moderator, but I cannot hear the room. So one possibility would be you could repeat the
We
questions
cannot
again.
hear you, Konrad. Just wait a minute.
You cannot hear me.
We cannot hear you. درست صدا هست؟
So I can hear the room. But no, I cannot hear. Okay. I think the people online can hear me, but I think the room can't. Sorry about sorry about that. Okay, cool. Thanks so much. Wait,
Konrad, can you hear me?
yes.
Okay, we don't have your voice.
I don't know what happened to my voice.
Okay, thank you for your interesting talk and also your sweet British accent. Uh, well, I don't know, have you ever been told, but yeah, that was really sweet. Uh, how do you perceive the future of neurocausality in the light of AI and ML, especially in the field of medicine?
Great. Um, just this is a great question. I just briefly want to make sure the room hears me or the room still doesn't hear me. Okay, I hear some arms. I see some hands. I'll assume that people can hear me. Okay, cool.
Okay,
So
I'm here, white coat.
okay,
Here.
cool. Oh yeah, I do see you. Wonderful. Okay, yeah, which means that you do hear me. Wonderful. Let's first talk about like the blind spots. So I think the blind spots is the same. So AI doesn't understand causality at all. So what we do is we fit predictive models, not like take ChatGPT or something. It's a predictive model of what the next word may be. It doesn't. It's only causal in the sense that it imitates the causal understanding of humans. It's very bad at figuring out if something causes something. In fact, because it imitates humans, it will wrongly make the same mistakes that humans do. So ChatGPT and all other AI models by default will basically confuse correlation with causation the same way that people do because that's what they've been trained on. So so causality is traditionally a blind spot, arguably the blind spot, and that's why clear is emerging. So clear is a conference where you have people within the AI who basically look at causality and are saying, hey, like none of the things we're talking about actually work at figuring out what causes what. There's a lot of things there that AI just can't do, and like the distinction between correlation and causation is the core of what makes causal inference possible. And and it has no notion of that. It's all our AI systems. They're just prediction engines. They don't understand. Not like I think humans are born, and it's really exciting if you have like a little 3-year-old kid. In fact, even if you have a 6-month-old baby, it thinks about the world in terms of causes and effects, and it wants to hear
Yeah.
from its parents explanations of basically how stuff works causally. If you ever tell like a story to a kid, it's always about like causally, this
Mhm.
happened. I did this, I was mean to that person, and then they did that, and then that happened. So um I think we are causal engines as humans. I think today's machine learning systems are not. And if you look at machine learning in medicine, oh, we have so much data. It's been entirely useless. If I really challenge all of you, find good actually happening application of machine learning in medicine. The best ones that people can come up with is, yes, we cannot transcribe what the doctor says, but we don't know which things cause which diseases. And you'd be like, well, buddy, we can read through a million papers. Well, but like the AI systems are built in such a way that they can never get at what causes what. They can easily find out what people like and believe. And so in that sense, so hold on. I only answered half of your question. I apologize for that. The other half was within neuroscience. And like I think in neuroscience there is a push where people say, well, why don't we like go and use optogenetics because we now have those techniques to perturb and see what's happening. And I think there's a lot of that being scaled up at the moment. So I'm hopeful both in AI because this community is coming, and in neuroscience. And look, the neuroscientists start talking about it. So Nicole Rust recently had a paper. I don't agree with all aspects of it, but like us as neuroscientists start to engage with it, and once we start engaging with it, we will find ways of solving it.
You mean that? Oh my god! You mean that? I'm standing just right there, big giant speaker. Uh, well, basically, let's give you an example. I mean, let's say I'm gonna go and open ChatGPT, and I'm asking him or her, well, give me the cause of I don't know, uh, colon cancer, or just map for me the causality of colon cancer, and I don't know, cigarette. I mean, but with this thing that you just told us, you say that it's not possible, right? It's not possible for AI to understand this.
This right, exactly. So what ChatGPT would do is it would take whatever most humans have said in its database and would go with that. But that's not what we. It's kind of, it can't do science because science is to find out the causal relations in the world that we don't understand yet.
Yes, thank you. And just can we have your? Uh, I mean, I don't have any question. Thank you for your answers. And I'm just really interested to know more about this and to be getting contact. If you give us, I don't know, an email address or something to can get in contact more.
Of course, my email address is. You can find it online, but I can type it here. Here's my email address. Um, yeah, these are exciting times. So for all of you that you're early in your careers, people are always worried that fields stop moving or stop being interesting, but the opposite is happening. And ChatGPT will change how you all operate as scientists. No, it's super helpful. Uh, but it won't make the job of the scientist go away anytime soon. I promise.
Thank you so much.
Hello, Konrad. Can you hear me?
Yeah, very well.
Great. First of all, thank you for your great talk. And I wanted to say that I'm a Neuromatch Academy alumni of 2022. It was a great experience for me.
Oh,
Uh,
wonderful. Thank
I
you.
have two questions. First of all, is well, you talked a lot about confounding variables and colliders, but I want to know how can we identify these variables, especially in large populations of neurons and agents? Like, for example, can we do things like, for example, looking from a higher perspective, for example, grouping the population, looking at a population of neurons, for example, looking taking an average over a certain region, and then saying, uh, for example, how neural information processing can move from from a stimulus to an action, and move from one region in, for example, the visual cortex to the motor cortex, and so on.
Yes. So what you're asking for is a very important question to which we don't have an answer. And let me unpack that a little bit. And let me make sure that everyone's on board there. I think we have a good notion of causality when we talk about individual neurons that are right next to one another. No? Like this neuron fires, we have an excitatory potential, that neuron is more likely to fire a little bit later. But what we really want to do is often, in particular in cognitive science, is not talk about neurons that interact with one another. We can't even record them. There's so many in the brain. But brain regions, how they connect with one another and how they interact with one another. And there's a lot of mathematical research that has never been done, which is if I have my local interactions and I can make statements about it, causal statements, say, under which circumstances will properties that are locally true still be true at the macroscopic level? No, you can say, what if we, instead of recording 100 neurons, we record 100 brain regions, and each brain region contains 1,000,000 neurons? Now, you can say there's probably conditions where the average, say, time delayed correlation from one brain area to another is an estimator of how many meaningful, effective fibers like go from one place to another. There's other conditions where that's not the case. No one, to my knowledge, has written out under which circumstances the things that we can observe macroscopically are true microscopically. And this is something, I mean, given that you were a neuromatch student, I want to, like, for anyone who's so inclined, in the neuromatch tutorials, we have this, we have the simulated dynamical system. Now, you can easily give it a notion of brain areas where you can basically say, well, yeah, let's make that matrix be mostly block diagonal because we have lots of connections within a region, little between it. And then you can say, if you generate the data like this, which is just like a few lines of change there, and you, instead of recording from all neurons, you record kind of averages of all the neurons within one neuron. How good is that at approximating kind of the off-diagonal connections between brain regions? This is a space that no one understands, which is weird because there's a lot of research in MRI that deals with or that talks about how brain regions influence one another. But we kind of have no evidence that we at all get causally even better than chance signals.
Great. Thank you for the answer. And I have another question. In your slides, you, first of all, it was the slides from Neuromatch Academy from the adjacency matrix. You added an epsilon sub t, which was a white noise, right? So,
Right.
and you said, for example, as the number of nodes in the neurons increases, we have more noise in the system, which leads to lower correlations, and eventually we can say that correlation cannot imply causation. So, I have a question: if we remove the epsilon sub t, so we have an abstract, completely causal system. Can we say, for example, in that system that we have 100%, well, definitely it's going to have 100% correlation. And can we, in that case, say that 100% correlation can imply causation?
You mean if two nodes were identical?
I mean, for example, I mean exactly like if we remove the entire noise in the system, we have an abstract system. So
Okay.
can we say that, for example, that is a causal system?
I wouldn't see why it would be a causal system. Like you can have, so you can have confounding in a fully deterministic system. Let's say every clock, and if it, not like you could have a system where there's no noise added at all, but sigma, that nonlinearity is a step function. That's then like a Hopfield network type things, Hopfield network type thing. And you can then see how it evolves, and it would still be confounded. You can never distinguish A influences B versus C influences A and then B. I mean, unless you have strong temporal knowledge. For example, if everything is guaranteed to have only delay one connections, then you have fewer at least the further past falls out, which isn't the case for brains. But even there, it's not identifiable generally. There are
when we
probably
say
conditions under which it's identifiable. Now, for example, if neurons switch state extremely rarely, then it's a little bit as if only ever one neuron is active at a point of time. And then I think it does become identifiable.
hello. Oh, okay. So even in a system with 100% correlation, we can still have confounding variables, and we cannot determine causation correctly, right?
That is the
Thank you very
that's the
much.
generally correct statement, I think. But again, like in a lot of real world scenarios, there are special cases where things work. What like maybe if you know that it's just a chain of variables, things might become identifiable. I have to think more about it. But here's a recommendation for anyone interested in causality. There's a book by Julia Powell. It's called Causality, which is wonderful for the mathematical details that it brings. And there's another book by Julia Powell that's called The Book of Why, which is great at intuitively explaining causality. And it really helps people kind of wrap their head around it. And it took me a surprisingly long time to kind of really understand the depth of causality.
Thank you very much, Konrad, for the interesting talk. We have also a panel that the link is available in the chat box if you consider it. So everybody is interested to talk more with Konrad and ask questions. Please go to the parallel room, I don't know, 1 or 2. The parallel room, and it's in the online link. And the room number 2, everyone wants to ask question can go there.
So just to make sure I get this
And we
right.
thank you again for the interesting talk. Thanks.
Great. I click on the
You click on the
SNS.
link.
Okay.
Click می‌تونم.
Okay, great. I was ask.
باشه. Okay, باشه. باشه. So we end this session here and bye with Konrad. Okay. See you in the
Okay, see
panel.
you there.